Did you know? The length of an object that is moving varies when measured from different points of reference. But why is that? And which one is actually correct? In this video, I will not only answer that question, but also prove it mathematically and give you a real-life example that happens every second. And at the end, there is a simple test for you so you can test your understanding. On the most basic level, if you remember from the last video, we proved when you move, time slows down for you. The faster you move, the slower your time ticks. It turns out that moving affects not only time, but also length. But don't just take my word for it. Let me show you why that is. Let's imagine Bob is on a train which is moving at a constant velocity v. In the train, Bob has a bulb on one side and there is a mirror on the other side of the train. The bulb turns on for a fraction of a second and then turns off again. The light from that bulb travels along the train, reaches the mirror, gets reflected, and travels back to its initial point. We can calculate the total amount of time that the light has traveled from Bob's perspective very simply. Let's call the length that the light has traveled from Bob's perspective delta x naught, and the total time it takes from his perspective for the light to complete the round trip delta t naught. We know to calculate time, we need to divide the total distance by the speed of light. So 2 delta x naught divided by c. Okay, that was from Bob's perspective. But Emily is also watching Bob from the platform. From her point of reference, the train and everything inside it are moving. The length of a train for her is delta x. When the bulb emits the light, the train is already in motion. So by the time the light reaches the mirror, the train has moved a certain distance. That means the light has traveled a distance greater than the length of a train. This extra distance is simply the velocity of the train multiplied by the time period in the forward direction, which is delta t1. So now the light is going to get reflected. But as the light travels backward and reaches the initial point in the train has also moved forward. The distance the train has moved is v delta t2, where delta t2 is the time period for the light to travel from the mirror back to emission point. Now to calculate the time period for the entire event for Emily, like we did for Bob, we need to calculate the time periods separately. Delta t1, again, is the time period taken by the light in the forward direction to reach the mirror. We know time is distance divided by speed, and here the distance is this black line. Now, on the reverse strip, the time period it takes for the light to get reflected and return to the point where it was emitted is delta t2 equals delta x minus v delta t2 divided by c. Minus because here the train and the light are moving in the opposite direction from each other. After a bit algebra, we get this. We can do the same thing for the other side as well. So now that we know how long it takes for the light to reach the mirror and return to its initial point, we can calculate the total time period for Emily. So we simply have to add these two together. In the last video about time travel, we calculated the formula for time dilation. Substituting what we calculated for delta t into that, after some algebra, we get the holy formula for length contraction. This helps us determine how much an object's length is shortened when viewed from different perspectives. Now that we know that, let's go back to the situation we had at the beginning of the video. Let's say Bob is in his spaceship, moving in a straight line. He measures the length of his spaceship while he's moving. The length of an object when measured while we are at rest relative to it, as Bob is in this example, is called the rest length or the proper length. For Bob, the spaceship measures 200 meters, but the spaceship is also moving at 80% the speed of light relative to Emily. What would the length of a ship be from Emily's point of reference, who is stationary and watching Bob pass by? Using the formula we derived together, we find that spaceship's length from Emily's perspective is 120 meters. So Emily sees Bob's spaceship passing by and observes its length at 120 meters. But still the question remains, who is right? 200 meters, or 120 meters? They are both correct. The length of an object depends on its speed when you measure it. Moving objects are shortened, but only in the direction they are moving. If the object is moving left or right, its height remains unchanged. Similarly, if the object is moving up or down, its width stays the same. The main takeaway is that there is no such a thing as an absolute length. Everyone can measure the same object differently depending on their frame of reference. Now, let me give you a real-life example of length contraction happening every day. Do you remember the muons example from time dilation video? We said that muons only live for 2.2 microseconds and they travel at 99.99% of speed of light. Even though they are moving very fast, 2.2 microseconds are not enough to travel 20 kilometers. Since they are moving so fast relative to us, from our perspective, their time should take slower. We calculated it, and indeed it was. So instead of 2.2 microseconds, they live for 155 microseconds from our perspective. And that's enough time for them to cover the distance at that speed. But that was from our perspective. From the muons perspective, their lifespan is still 2.2 microseconds. So how can muons cover that distance from their perspective? We know the speed and the time, which results in a 46 kilometers distance traveled at that high speed. The proper length here is 46 kilometers. That's the distance we, as the stationary frame of reference, see the muons travel. Given the information we have from both perspectives, we can put them into the equation and figure out how far the distance was from the muons perspective. It comes out to 650 meters, meaning that from the muons perspective, not only do they live for 2.2 microseconds, but the distance from the upper atmosphere to the Earth's surface is only 650 meters. So, not only is the length of an object shortened while it's moving, but the distance from the moving observer is also shortened. Now, are you ready for the quiz to test yourself? Emily just turned 18. She wants to celebrate her 90th birthday in Velora planet. But that planet is 1 billion light years away. Can she make it? Can she travel a distance that takes light 1 billion years to reach in 1 year? I will post the answer and full explanation in the community. You can join today for free, link in the bio.